So my name is Manu Fried. I'll be the chair of this session. And we will have 3 lectures in this session. So each lecture of 45 minutes. And so we will have some space between the lectures. Between the first and the second, there will be just a short time, but between the second and the third, there will be a little more time. There will be a break of half hour. And so our first speaker will be Professor Amit Singer from Princeton University. So Professor Amit Singer got his PhD in 2005 from Tel Aviv University, Israel, from Ziv Schuss. From 2005 to 2008, he was Gibbs Assistant Professor in Applied Mathematics at the Yale University, Since 2008, he is in Princeton. He has received some distinctions, and many distinctions, and I quote just a couple of them. So in 2012, he received the Simons Investigation Award, and in 2014, he received the Moore Investigator Award. So Singer works on a broad range of problems in applied mathematics, solving specific applied problems and employing sophisticated theory to allow the solution of general class of problems. So recently he is working on cryo-electron microscopy. And today he is going to talk exactly about the mathematics of cryo-electron microscopy. So please welcome Professor Amit Singer.
Okay, thank you very much for the kind introduction. It's a pleasure to be here. I really enjoy this wonderful city and Congress. It's my first time here. Before I begin, this is working. Okay. I would like to dedicate this talk to my advisor, Zev Schuss, who passed away just 2 weeks ago. Zev was a really remarkable, not just mathematician, but also as a person. He was very, very generous. Actually, the picture that you see here, I took it when in our joint office in Chicago, when I spent with Zev a few months together. And I just wish that I can be as generous and dedicated to my students as Zev was to me and to all of the students. Zev had a remarkable life, and I will not tell him today his whole life story. I just want to mention, you've seen in the previous slide that he was born 2 years before World War II, and when he was 2, he was born in Poland, and in the beginning of the war, he started a very long journey that you can see on the map here. Starting in Poland, all the way to Siberia, to Iran, and eventually when he was 5.5, long parts of this trip he did by himself without his mother or father. He eventually got to Israel. So he really had a remarkable story, and this is just a poster from his 80th birthday conference that we organized to him in the IMU, which is the Israeli Mathematical Union. So back to cryo-electron microscopy and to modern days. This is actually just a few months ago, in late October, the 2017 Nobel Prize in Chemistry was awarded to Jacques Dubochet, Joachim and Richard Henderson for the development of cryo-electron microscopy, which both simplifies and improves the imaging of biomolecules. And the last sentence is really crucial. This method has moved biochemistry into a new era. So for those of you who know something about structural biology, you probably are familiar with X-ray crystallography, which there are numerous Nobel Prizes awarded with X-ray crystallography. Perhaps the most well-known one is the double helix structure of the DNA. But there are many, many molecules of biological interest that nobody knows how to get them to crystallize. They withstood all attempts to crystallize them. And cryo-electron microscopy completely bypasses the need to crystallize molecules. So the Nobel Prize was not a big surprise for those who are following journals like Nature and Science. So this is from Nature a few years ago. The revolution will not be crystallized. So move over X-ray crystallography, cryo-EM is kicking up a storm in structural biology by revealing the hidden machinery of the cell. Or this is Science 2014, the resolution revolution. So in green, you'll see advances in detector technology and image processing are yielding high-resolution electron cryo-EM structures of biomolecules. And in early 2016, the journal Nature Method selected single-particle cryo-EM as method of the year 2015 for its newfound ability to solve protein structure at near atomic resolution. So why cryo-EM? So as I mentioned, it's a method that allows to get molecule structure at near atomic resolution without crystallizing the molecules. So it's a very general technique. And it has another major advantage is that it images single molecules. So unlike X-ray crystallography, where you get diffraction patterns that correspond to aggregation from all molecules in the sample, and then it's very difficult to understand and analyze, say, conformational variability of those molecules that can come in different shapes and conformations, because everything is average in the measurement. In cryo-EM, you can measure single molecules. So potentially, you have the ability to map the energy landscape of the molecule, the conformational space. Why now? Cryo-EM is not a new method. It was invented at least more than 40 years ago. But only in recent years, say in the last 5 years, we are witnessing a revolution. And the revolution is that now we can get to high resolution. And this is due to advancement in detector technology. So actually, we can take movies and get much better signal-to-noise ratio for our images. I'll not get to this today, because there is not enough time for that. For this audience, I would like to mention that the reconstruction process is entirely computational. So once data is acquired, everything is done by computers and algorithms and software. And there are actually enormous opportunities for mathematicians, applied mathematicians, computational mathematicians, and even pure mathematicians. And I hope that my talk today will incite some of you to look at this fascinating area. So how does cryo-EM work? The process is very simple to explain. What you see here are not true molecules, it's just artist's concept. What they do, they freeze molecules in a very thin layer of ice. The ice layer is so thin that you can assume that there is just one molecule. If you look in the vertical direction, there's just no room for two molecules to sit one on top of the other. And they freeze the molecules using liquid nitrogen. At the moment of freezing, every molecule just picks a random orientation and a random position within the ice layer. And then you shoot an electron beam perpendicular to the ice layer. The electron beam goes through the molecules, through the ice, and beneath you have a film or a camera, a detector. And the intensity of the pixels is proportional to the integral, basically to the path integral of the electric potential created by the molecules. So the molecules are made of charged atoms, and they create an electrostatic potential. And what you observe are two-dimensional tomographic projection images of the 3D electrostatic potential. The first step is usually some kind of image segmentation. So you crop particle images from a big image called a micrograph. And then the standard reconstruction problem in cryo-EM is an inverse problem in which, from the micrographs, you want to predict the 3D structure of the molecule. Now, in cryo-EM, in single particle cryo-EM, you have one image per particle or per molecule. And the reason being is radiation damage. So as the electron beam goes through the molecule, it breaks the chemical bonds that make the molecule. And if you really want to get to high resolution, to atomic scale resolution, you are very limited by the amount of electron dose that you can bombard the specimen. And so you have only one image per particle. So more mathematically speaking, we have So we have a molecule, say, that we characterize by a function phi. So phi is the electric potential created by the molecule, and that's the function that we'd like to estimate. And we'd like to estimate it from many images. So II, let's say it would be the ice image. X and Y would be local coordinate system of the image. And the XY pixel is nothing but, as I mentioned before, the integral in the direction of the beaming electrons. Let's say this is the Z direction, after you rotated the molecule by some unknown element of the rotation group SO3. And there is another convolution operator floating around here that, for the purposes of today's talk, I will ignore. This has to do with electron diffraction theory. And it's related to the contrast transfer function of the microscope. But I will not go into this today. So the reconstruction problem is an inverse problem in which you want to estimate phi from n noisy projection images. And noise comes from the fact because of the radiation damage, because you have very few electrons per pixel. The heterogeneity problem is a much more, let's say, ill-posed inverse problem in which you want to reconstruct per n structures for your n images. So you can say, okay, how is this going to be even possible? How can one reconstruct n 3D structures from n two-dimensional images? So this will become well-posed only if we put some under regularity assumptions. So can we even solve the problem for clean images, even without discussing noise? So this is just an illustration where I show you 12 projection images, clean projection images, and then the question, can you guess that it was actually taken from this 3D structure? So if you've seen maybe enough Disney movies, you can make this guess, but otherwise, it seems a bit complicated, okay? Because you don't know the viewing directions associated with the images. So there is a very basic tool from tomography that allows to solve the reconstruction problem, at least for clean images, which is the Fourier projection psi theorem, that says that if you take a 2D projection image, of a 3D object and then take its 2D Fourier transform, then the 2D Fourier transform is nothing but the restriction of the 3D Fourier transform of the 3D object to a slice, a planar slice that goes through the origin and residual space, and whose orientation is exactly the orientation at which you've taken the image. So in classical computerized tomography, in CT, say medical imaging, when the machine knows exactly the viewing directions at which it imaged a patient who was instructed not to move for the duration of the imaging process, you can collect those slices and then do 3D Fourier inversion and get the object in real space. But in cryo-EM, we somehow need to organize the geometry. All the images are scrambled. We don't know the viewing directions, and now we need to somehow order them. So very, very basic elementary geometry comes to our help in the form of common lines. So now that we know that every projection image corresponds to a two-dimensional plane going through the origin of this 3D residual space, we know that every two planes intersect at a line. So we have the property of common lines. So between any two images, we can find the common line of intersection. Say if the images are clean, then by just brute force search, we can try to correlate all lines in one image with all radial lines in the other image. And let's say that the values of the 2D Fourier transforms on those red lines will agree. So this gives us 2 out of the 3 degrees of freedom of Euler angles, let's say. The only degree of freedom left undetermined is the angle between the two planes. And so to determine the angle, this leads us to the mid-80s, one can look at the common line pairs between 3 images, and those uniquely determine the relative orientations between the orientations of the associated molecules, obviously up to a global rotation and up to a global reflection. So in cryo-EM, in single particle cryo-EM, it's never possible to get the handedness or the chirality of the molecule. And the reason being is that if you look at projection images of my right hand and projection images of my left hand, they would look exactly identical. So unless you do some other kind of field series experiment, you'll never be able to tell the chirality of the molecule. So angular reconstitution, the method that uses 3 images and then maybe adds a 4th one, a 5th one, uses common lines, is a beautiful method that shows that you can solve the cryo-EM problem with clean images, but what about noisy images? In the experiment, we get very noisy images. And so here I just show a simulation where I simulated on the computer clean images, clean projection images, and just contaminated them with wide Gaussian noise, a different level of SNR. And SNR of 2 to the minus 6 or 2 to the minus 7, I'll show you later experimental images, resembles what you see in the experiments. And let's see if angular reconstitution can solve the problem with such level of SNR. And you see that as a function of the SNR, as the SNR goes down, our ability to detect common lines reliably also goes down exponentially fast. So 2 to the minus 6, 2 to the minus 7, only about 1 in 10, say, common line pairs we actually detect accurately. Which means that you should be extremely lucky. Say only 1 in 1,000, 3 pairs of common lines are going to be accurately detected. And even if you're so lucky, then the 4th image, 5th image, and so on, at some point you're going to make errors, and those errors are just going to accumulate. So how to solve the cryo-EM problem at low SNR if angular reconstitution does not work very well? So one way is to try to improve those common line approaches. And I and others have worked very hard on this approach using methods that come from, like approaches that come from other areas, like theoretical computer science, using semi-definite programming that have been used for completely other problems, like approximation for problems like max cut in graph theory. Or we tried ideas of that relate to synchronization of rotations. And this certainly helped a little bit. We also try to improve the image quality, just to apply denoising for the images and boost the SNR. For example, by averaging every image with other images that we believe was taken from the same, or relatively the same viewing direction. And for this, again, we apply some sophisticated machinery, like invariant representation of the images, that is representation that is invariant to image rotation and translation, so we can build a graph of the images very quickly, and then we applied methods related to what Rafi Koifman talked about earlier today of diffusion maps. And again, this helps a lot, especially for large molecules, for which the SNR is not that bad. But I want to make the point now that estimation of rotations, no matter how sophisticated you are about the algorithms, is actually impossible at very low SNR. So there is an SNR below which any algorithm, no matter how sophisticated you are, and even if you have like exponential time at your disposal, is not going to work. And to convince you that this is the case, just consider an oracle that knows the 3D structure. And I'll try to convince that even that oracle cannot estimate rotations. So what the oracle would do, so the oracle can just take this 3D structure and project and get 2D images, projection images at all possible viewing directions. And now, given a noisy experimental image, the oracle can do projection matching, can take the noisy projection image and try to find the best match among the clean templates. Now, just because of the noise in the experimental images, the correlation value is going to fluctuate. There are going to be random fluctuations just because of the noise. And so even the oracle is going to very often make mistakes and assign completely wrong rotations to the experimental images. So if the oracle cannot estimate the rotations accurately, you shouldn't expect us with computers to do better than that. Now, luckily, the structural biologists, they care nothing about rotations. So the only reason why I and others started trying to estimate rotations is because we're mathematicians, and we're trained to solve problems by, okay, we already know how to solve the 3D reconstruction problem. That's a solved problem in computerized tomography, in medical imaging, in other fields. So let's try to estimate rotations, and then this is a solved problem, we're done. But structural biology, they care nothing about the rotations. For them, they're just nuisance parameters. These are not the parameters of interest that they care about. So viewing angle, shifts, they don't care about it. They only care about the 3D structure. So the fact that we cannot estimate the rotations does not mean that we cannot estimate the 3D structure, even if we cannot estimate the rotations. And I want to convince you that this is indeed the case. And actually, we can do 3D reconstruction at any SNR, no matter how bad is the SNR, given enough images. And in the process, we'll try to understand how many images are really needed. What is the sample complexity of the problem? So when you're faced with a statistical estimation problem, you go back to what you learned in Statistics 101. And the first method that I think, at least I learned, is the method of moments that go back to Pearson. It's very easy usually to compute, and it's consistent, meaning in the limit of large enough samples, you get to the right value of the ground truth parameter value. It's theoretical normal, but it's not optimal. Okay, there are better estimators in the sense that they have smaller variance, like maximum likelihood that it was introduced by Fisher a few decades later. Maximum likelihood is usually harder to compute, but under certain technical conditions, it is optimal or efficient. Okay, so it's asymptotically efficient. It has the smallest variance when you're at the large sample limit. And there are other related methods that go by the name of Bayesian inference that I will not go into, but if you have some good prior about your parameters, then you can definitely do better. Today, maximum likelihood estimation is what almost everyone uses in the field of cryo-EM. So this was introduced to the field by Fred Sigurs from Yale at around 98. And the software that people use today it was written by Sheres from Cambridge at 2007. It's called Relion. And in Relion, basically, what is being done is just an expectation maximization algorithm where all the nuisance parameters are marginalized over. So like I mentioned before, you cannot estimate those parameters, so you marginalize over them. And there is an E step and an M step. I don't really want to get into it very much. Just in the E step, you do projection matching, just like what our Oracle did, but you assign weights. You don't try to do hard assignments. And in the M step, it's just a weighted tomographic reconstruction. The EM requires an initial model, and convergence may depend on that model. So this is a very non-convex optimization problem that if we try to find the maximum likelihood. And there is no guarantee that we'll converge to the global maxima, only local one. And indeed, people have observed that convergence can depend on the initial model. Now remember that we don't have any ground truth. So if one structural biology lab can get one molecule, another a different molecule, and they will fight, and there is no way to decide which one is correct. And also, EM is slow. You need several passes over the data until convergence. And today there are many heuristics, and people use GPUs, and definitely help. But it's still quite slow, especially if you try also to solve heterogeneity. And the last point, especially for this low density, it's very difficult to analyze mathematically what's going on in EM. So for example, a very basic question like how many images are needed in order to be able to do reconstruction as a function of the SNR. So we'll try to answer this question. And if you go back and look at the method of moments, it gives you a direction to answer the question. So for some of you who are not very familiar with method of moments, a very quick introduction. So for example, if you try to estimate parameters that correspond to a mixture of two Gaussians, so the sample data is coming from a mixture of two Gaussians, so there are just 5 parameters, the mean and variance of the two Gaussians, and the proportionality of them. And the way you can estimate is by just computing the first 5 moments of your samples and then trying to fit the parameters. And this was actually done by hand already in the 19th century by Pearson. And Pearson used one more moment, the 6th moment, in order to pin down the parameters exactly. And the nice thing about the method of moments is that you just need one pass over the data. And you don't even need to store the data. You can do it in a completely streaming fashion, unlike EM, where you have to revisit the data again and again. So can we do method of moments for cryo-EM? So what would the moments mean in cryo-EM? So the first moment will just be the average image. You take all the images and average them. This will be just an image. The second moment is very much related to the covariance matrix of the images. So you just take, so now it will be a function of 4 variables, say x and y of one pixel and x and y of another pixel. And similarly, you can go to third order moment and so on. And a question is, can we estimate the 3D structure from those moments? And how many moments are required? Can we reconstruct from one moment? Well, obviously not, because we need the 3D structure, so just an image is not enough. But maybe second order moment is enough, or do we need a third order moment? Who knows? And computationally, we need some way, both computationally and statistically, a way to deal with those moments, because they grow fast very quickly. Okay? If you look at the third order moment, for example, naively, it looks like being 6-dimensional. So if you are looking at a molecule size 100 by 100 by 100 voxels, 1 million voxels, and the third moment is not very pleasant to work with. Okay, so it will be like 10,000 by 10,000 by 10,000. So there is, first, a very simple simplification that we can look at symmetrized version of those moments. So for example, we can take all our images and take all their in-plane rotation and just average them to create a radially symmetric average image, which is just one-dimensional. So either you do it to the images that you acquired, or you can just assume ahead of time that the distribution of rotations is invariant to in-plane rotations. For example, you can just rotate the detector, and this should not change the distribution. So in that case, the first moment is one-dimensional, and the second moment is, instead of being 4-dimensional, now it depends only on the 2 radii and the angle between the 2 pixels, so it's 3-dimensional. Another question, if we are lucky. Remember, we're trying to estimate a 3-dimensional object, the 3D structure of the molecule. And we see that the second moment is also 3-dimensional. So maybe we are lucky, and just by doing principal component analysis, PCA, estimated the covariance matrix, we are done. Somehow it encapsulates enough information about the 3D structure. So let's see if we are that lucky. Well, 40 years ago, there was a really fascinating paper by Tzvi Kam of the Weizmann Institute in Israel, who proposed a very, very similar method that was completely forgotten by the community. So this is like one of the papers that are way ahead of their time. And what Kam suggested in our language today is basically to compute the covariance matrix, if you wish, of the 2D images, and to see what you can extract from that covariance matrix about the 3D structure. So let's see if I can now convince you just with my hands, okay, that when you compute the covariance matrix of the 2D images, if the distribution of rotations associated with the molecules is uniform over SO3, that is, it's taken from the Haar measure over SO3, then the covariance matrix is really equivalent to computing the autocorrelation of the 3D Fourier transform of the molecule with itself. So it's equivalent to the autocorrelation function. And the reason being is that, remember that we can consider images in the Fourier domain. When we correlate any two frequencies, this corresponds to some 2D frequencies in 3D that you correlate, you just multiply them. And now every image will correspond to 2 different 3D frequencies, but they are all related by a group action. So now, when you sum all over them, basically what you've done is Monte Carlo integration over the rotation group SO3. Monte Carlo integration of what? Of just the Fourier transform of the molecule times itself. This is the autocorrelation function. So there are good news and bad news. We now know how to relate the covariance matrix to the autocorrelation function, but the bad news is that we know that the autocorrelation function is usually not enough to recover the signal. This leads to the very famous phase retrieval problem. For example, if you look at one-dimensional signals, where you know the autocorrelation function, you know the power spectrum of the signal, but you don't know the phases of the Fourier transform. The right language, in our case, is to use spherical harmonics. So if you look at the spherical harmonic expansion of the Fourier transform of the molecule, then the coefficients, the ALMK, okay, these are function of the radial frequency. These are the unknowns that we try to determine. And what CAM showed is that you determine them only up to some Cholesky decomposition, namely that from the data you can compute these matrices, the CL, K1, K2. For every order of the Fourier of the spherical harmonic expansion, you get this matrix. But we know that the Cholesky decomposition is not unique. You can insert here any unitary transformation. And because we know that the molecule is real valued, it happens to be just an orthogonal matrix. So this may mean that we need third order moment if the distribution of rotation is uniform. So in my group, we've read quite a lot on trying to do covariance matrix estimation accurately and fast. I will not go into the details. I just want to mention some highlights that we can include steerability, that is, include all images and all their in-plane rotations, but do it not in a naive way. And we can do CTF correction, what I mentioned before about the constant transfer function. But more importantly, when you do covariance estimation, you notice that there is some random matrix theory that plays a very important part. That if you ignore, you do very poorly in estimating the covariance. And there are many interesting works in the literature of statistics in high dimensions. People like Ian Johnston and Dave Dono and many others, Matan Gavish, that propose really useful eigenvalue shrinkage procedures. It's too bad that I don't have time to talk about this, but it's a very important take-home message for those of you who care nothing about cryo-EM, but do want to use PCA and covariance metric estimation in the work. Okay, so we've seen that second order moment is insufficient. There is recent work by my former student Afonso Bandera and his co-authors that show that third order moment is actually sufficient for reconstruction, but I don't like third order moments. And the reason I don't like it is that, first of all, it requires more images. If you think about second order moment, when you multiply pixels, the SNR now deteriorates by a lot, because the variance, if the variance before was sigma squared, now it's sigma to the 4. And if you look at third order moment, now it's sigma to the 6. So we'd like to avoid third order moments. Also, it has much higher dimensionality, so from computational point, we don't like it so much. And also from the statistical estimation point of view, at least I'm not familiar with very theoretically profound eigenvalue shrinkage procedures for tensors. Okay, so we'd like to avoid them, at least for now. So it seems to us, at least when I talk to you today, this is still work in progress, that if the viewing directions are not uniformly distributed, so let's say if the molecule has some preferred orientations, then second order moments are actually sufficient. Okay, we win from the fact that the distribution of rotation is not uniform. And actually, if you look at data and most reconstructions that have been done until now using expectation maximization, look at the distributions, they are typically not uniform. And the way we do it is by, it leads to a system of polynomial equations. So if you write down what is the covariance matrix, it depends on the 3D structure quadratically, and linearly on the distribution. So you have third-order polynomials of degree 3 that you need to solve. And it's a very non-convex optimization problem, but we seem that like typical non-convex optimization methods work quite well for this problem. And I just outlined the procedure. What you do, you take 2D images, you do PCA, eigenvalue shrinkage, and so on, and then method of moments give you the structure. Okay, so this is just one figure to summarize the procedure. And from the point of view of sample complexity, it shows is that we just need number of images to scale as 1 over SNR squared. Okay, usually in statistical estimation problems, you need just 1 over SNR. Number of images or number of samples should scale as sigma squared. But because the rotations here are unknowns, there are these latent variables, you see that the sample complexity jumps to 1 over SNR squared or even to 1 over SNR cubed if the distribution is uniform. Finally, I want to talk about the heterogeneity problem, which is a very ill-posed problem. So to remind you now, to every 2D image, there may correspond a different 3D molecular structure. And as I mentioned earlier, it sounds like impossible to get for every 2D image a different 3D structure. We lose information in the process. So usually there are some assumptions that people make. One is that the number of distinct conformations is just a small number. If you say 2 different conformations, 3 different dominant conformations, and then they will use the same expectation maximization maximum likelihood framework. Or we can also use the method of moments framework. Another assumption for regularization is that the conformation reside on or near a low-dimensional subspace or a manifold. So for example, if those molecules, if they are made of a few rigid bodies that can rotate and move, or they have maybe some flexible motion, then there is just a small number, finite number of degrees of freedom. So indeed, the data lies on a manifold in the same notion that Koifman discussed earlier in this talk today. So for large molecules, if you indeed assume that they lie on a low-dimensional manifold or a subspace, then you can first try to estimate the latent variables, even though I told you before it's impossible for small molecules. For large molecules, it is possible. And then we can even estimate the covariance of the 3D structure. That is, we try to estimate this low-dimensional structure. And what allows us to do that is, again, the Fourier projection size theorem. So for the sake of time, maybe I'll skip that, but if you want to discuss it with me how to do it, I can explain. It's much more ill-posed problem that now you really need coverage of the entire viewing directions. Unlike just 3D reconstruction, that you don't need that. In the low-rank approach, I want to convince you that it's very much related to problems that people regard as, and perhaps you've heard about metric sensing or low-rank matrix completion in recommendation systems, in other areas of science and technology, where, and to convince that this is indeed the case, you can write, say, the ICE 3D structure as some average structure plus a combination of what we call Eigen Volumes. So this would span the low-dimensional subspace, and there are just R of them. Now remember, so if you look at the matrix made of columns, where every column is just, say this would be the ICE column associated with the ICE image, then this matrix will be of low rank. And you can realize that what you're doing is a metric sensing problem by noting that the ICE image is just a tomographic projection of the ICE column. And so what you get is some linear sensing of this ICE column. And from those linear measurements, what you're trying now to estimate is the low rank matrix. but it's a very noisy version of the low-rank matrix completion problem. And we've seen that alternate minimization works quite well for the problem, but you have to initialize it carefully. And initialization comes from a spectral method that goes to the 3D covariance method that I skipped before. We also have a manifold learning approach when the 3D structures allow in a manifold rather than on a subspace. And then the idea is to use indeed methods such as diffusion maps and eigenfunction of the Laplacian in order to get an idea of what is the manifold of conformations. So what you do is that, again, starting from this kind of an expansion, now that you have those coefficients, say you did matrix completion and you have the coefficients associated with every volume, you can compare those and look at something like a Gaussian kernel and then build a graph, and you have the nearest neighbors, and you can compute the Laplace-Beltrami operator of this manifold and look at eigenfunctions. And because you assume that the 3D structure are actually smooth functions over the manifold, you can then expand them in those harmonics, if you wish, or in the eigenfunctions or the diffusion map coordinates. And this also works quite well. I'll show you data and movies shortly. So now, to finish the talk, I'm getting to the last part. I'm going to show you work both with simulated data and also work with experimental data. So the first experiment is with my former postdoc, Roy Lederman, who's just moved to Yale. And so what you'll see is just a cat, okay, that can move its tail and can move its head. And it's doing it at different times. So now basically you have, instead of a single 3D structure, you have a movie of 3D structures. So the right way to think about it is a function in 4 variables. Let's say the 3 spatial variables and 1 variable for time. And if there can be more degrees of freedom, and then you'll have even a higher dimensional manifold. So you can project the cat in different directions. You contaminate with noise, and we have 50,000 of such noisy images. The second data set is to show the case of compositional heterogeneity, when one part of the molecule remains static, rigid, and there are other parts of the molecules that move in time. And you'll see, okay, this is a very realistic assumption for some molecules. The last 2 data sets are experimental data sets, one from my long-time collaborator at Yale, Fred Sigurth. This for his ion channel. So this just gives you a glimpse on how images looks in reality. Okay, so there is a molecule here. Just so you understand the level of noise that we are dealing with. And this is another data set from our collaboration with UCSF, with Adam Frost. Again, these are much larger images, almost 500 by 500 pixels, just for a single particle. And there are about 100,000 of them. So Adams and his lab members have just published their work about this in Science. Again, I'm not sure if you've seen such images for the first time, that you should believe me that there is a molecule here. Okay, so now it's time to show the video. So the video will show results for each of those data sets. Okay, so this is for the cat, the synthetic data. So that's the ground truth, just the cat twisting the head, moving its tail. This is just to show you the cat from different viewing directions. So that's a reconstruction. Okay, so you see that we can actually do quite a good job in getting the major features of heterogeneity here, the continuous heterogeneity. I should mention that procedure based on EM completely fail for continuous heterogeneity, because there are just too many parameters to update here. Okay, this is what we call the pretzel. So we have one rigid static, the base of the molecule, and two parts that are moving, and this is the reconstruction. Okay, the real data sets, this is still work in progress. These are very, very messy data sets, and we get data sets for which nobody can solve for now. So that's a static object that we got using our methods, ignoring heterogeneity. This is for the ion channel. And finally, this is the data from UCSF. Again, what you see here are just two reconstructions at high and low resolution that we did. And we're starting to see continuous motion of that molecule. Okay, I think we can go back to the slides now. Okay, so in summary, cryo-EM is, at least in my view, on its way to dominate 21st century structural biology. So if X-ray crystallography dominated the 20th century structural biology, if you looked at biology departments and biomedical institutions, they all purchase now electron microscopes, and there is a huge transformation now. Even like people who got Nobel Prizes for their works in crystallography now switch to cryo-EM. I showed you that the method of moments paves the way to structural determination, just with a single pass over the data, and completely bypasses rotation estimation. And it shows us that reconstruction is possible at any SNR, and that the sample complexity scale with the SNR either as 1 over SNR, 1 over SNR squared, or 1 over SNR cubed, depend on the conditions. And we discussed the cryo-EM heterogeneity problem, which is widely believed as the most important and crucial open problem in the field, if you listen to Frank and Henderson, who got their Nobel Prizes. I would like to mention that we have an open source toolbox where you can play with everything that I talked about today, and if you want to get your feet wet. And finally, I want to put the last slide for my collaborators and former and current postdocs and students. And I would like to end the story that, last but not least, you see the name of Koifman here, who gave the plenary talk today. And I'm very thankful for Koifman for introducing me to the cryo-EM field. Basically, Koifman introduced Yoel Shkolnitsky, my longtime collaborator, who is now at Tel Aviv University, basically to talk with Fred Sigros, who is a biophysicist at Yale. And together we started this long-time collaboration. So thank you, Rafi, and thank you all for listening.
Okay, if you have any questions, just raise your hand, and the assistant will bring the microphone to you. Other questions? Okay.
Hi, thank you for the nice talk. I was wondering, since we know that the molecules are basically constructed from blobs or spheres, is that a piece of data that you can put into the algorithm to estimate a union of blobs instead of just estimating any 3D shape or 2D surface, boundary surface?
Yeah, that's a very good question. So if you want to get to not so high resolution, let's say 5 or 6 Angstrom resolution, then some research groups indeed put this assumption and write the molecule as a mixture of Gaussians. or a mixture of other nice basis functions, and this significantly reduces the number of coefficients that you need to estimate. So let's say instead of million coefficients for 100 by 100 by 100 voxels, you just need a few thousands. But if you want to get to atomic resolution, then usually people use a voxel-based, and then you're back to square one.
Any other question? If not, let's thank our speaker again.